Thank you for joining us for the Consulting Specifying Engineer webcast, Backup, Standby, and Emergency Power for Hospitals, sponsored by Cyber Sciences and Kohler. I'm your moderator, Amara Razgas, with Consulting Specifying Engineer and CFE Media and Technology, and I'll be with you for this hour-long education session. Let's learn about this platform. If you're having trouble with your slides or the sound, refresh your internet browser or click the Refresh Media button directly under the presenter's photo. You can control the volume settings by adjusting the volume on your own device. If you're having technical problems, click on the question mark at the top right corner of your screen to do some system checks before contacting an online technician. If you do need help, please type a message into the Ask a Question box and we'll respond in the Answered Questions box. To download the presentation slides, use the Event Resources on the left side of your screen. Type questions for the presenters in the Ask a Question box on the left side of your screen. You may ask questions at any time during the presentation, and the Q&A portion will start in 45 minutes or so. If you're interested in receiving one AIA CES approved learning unit for this event, you need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab option at the top of your screen. The quiz will open in a new browser window, so I recommend you open a new tab right now because the link will break when the webcast signs off. In keeping with the American Institute of Architects Continuing Education System Policy, please take a moment to read the Quality Assurance slide. Here are the learning objectives. We'll talk about these in today's presentation. Please note that any red underlined text you see is a hyperlink to the PDF where you can get more information. Now let's hear from this session's sponsors. At the conclusion of the commercials, you may experience a few seconds of silence to make up for mixed internet speeds. Please stay tuned after the videos for today's presentation.
In the healthcare industry, always-on power is key for patient safety and acute care. When a loss of power can result in patient injury or loss of life, failure to provide reliable power is not an option. And with ever-increasing disruptions in utility power, confidence in the emergency power supply system's ability to move from normal to standby power is essential. At Cyber Sciences, we provide precision timing for accurate emergency power supply system testing. Sequence of event recorders monitor and record the status changes of inputs from equipment, such as the automatic transfer switches, switchgear breakers, and uninterrupted power systems. This provides the confidence to know that the system is operating exactly as designed, or if any changes occur to the equipment over time, threatening system stability. For more information on products and services from Cyber Sciences, visit cyber-sciences.com/healthcare.
Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engines running. Commit. Liftoff. We have liftoff at 11 a.m. Eastern Standard Time.
All right, we have lined up two exceptional presenters today. Richard Vedvik is a senior electrical engineer and acoustics engineer with IMEG. Rich has experience in the healthcare, education, commercial, and government sectors. His electrical engineering experience includes lighting design, power distribution, emergency power systems, and fire alarm systems. He was a 2015 Consulting Specifying Engineer 40 Under 40 award winner and he is a consulting specifying engineer editorial advisory board member. David Stymest is a senior consultant with Smith Seckman Reed. He has many years of experience, and his background includes hospital facilities engineering. David is a forward-thinking, leading industry expert in the management, operation, testing, and application of emergency power systems in healthcare facilities. He's an accomplished speaker, trainer, and author who has presented at national and state conferences and has been published more than 50 times. I'm excited to work with both of you. David, you are our first presenter. You're live now.
Thank you, Amara. What I don't see right now is my first slide.
All right, David, well, you are sorting out your thoughts there. We'll make sure that you're on your first slide. Why don't you go ahead?
Okay, thank you. I'm required to tell you that you will hear some opinions today, and the opinions that you hear will be mine and not the official position of the NFPA or any of its technical committees, and shall not be considered to be nor relied upon as a formal interpretation. The reason for this is that I'm a primary voting member of the NFPA Technical Committee on Emergency Power Supplies, which is responsible for NFPA 110 and 111. Next slide, please. Today, I want to start off by talking about the authorities having jurisdiction, the different types of authorities having jurisdiction, and their impact on the requirements. I'm going to start with the federal agencies, the agencies of the U.S. government, including Department of Defense, Veterans Health Administration, the Indian Health System, and others. And these agencies, I'm not going to talk about one agency until I get to the bottom of this slide, but these agencies choose to be accredited by the Joint Commission. They're not required to be, except they've made the decision to be accredited by the Joint Commission. Because they do not report to CMS, which we will talk about in a moment, they're not required to follow the addition of the codes that CMS adopts. Generally, the federal agencies will adopt new editions of the Life Safety Code and related codes and standards shortly after the NFPA publishes those editions. The state and local authorities having jurisdiction, depending upon the state, depending upon the locality, sometimes adopt their own versions of the codes and standards. And because the codes and standards they're not documents that stay the same. Most NFPA codes and standards, the vast majority of them actually follow what CMS adopts, simply because it's easier. But there are state and local authorities having jurisdiction that will also adopt whatever edition of the codes and standards they wish to have. The building codes is also an authority having jurisdiction, as is any local, state, or national authority that adopts the Facilities Guidelines Institute and the FGI guidelines. CMS, which is the Centers for Medicare and Medicaid Services, is an arm of Health and Human Services. Most of you are familiar with Health and Human Services because CDC is another arm of Health and Human Services. The CMS is presently working from the 2012 edition of the Life Safety Code and the 2012 edition of the Healthcare Facilities Code. And with those two documents, those two codes also have hundreds of other NFPA codes and standards that they invoke. all of these requirements are not identical. They're not the same. And it's one of the reasons that if someone were to ask, well, what's the specific requirement for my system? It really depends. It depends upon the codes and standards. It depends upon the authorities having jurisdiction. The last CMS thing I want to talk about is the CMS Emergency Preparedness Final Rule. That was adopted by CMS back in 2016, and it applies to every single healthcare facility that gets Medicare, Medicaid reimbursement from the federal government. Next slide, please. The terminology that we need to understand is that there are differences. Unfortunately, to some, there are differences. NFPA 99 is the Healthcare Facilities Code. NFPA 99 basically states that it applies wherever healthcare is performed on humans, except in the home. NFPA 70 is the National Electrical Code. Both of these documents refer to an alternate power source. An alternate power source could be one or more generator sets on site, could be one or more battery sets on site. In some cases, if a healthcare facility, particularly governed by NFPA 99, is connected to its own generator system or a local generator system. When it occurs most frequently in large cities with a large number of healthcare facilities near one another. In those cases, the local generator can be considered to be the main power source for one or more healthcare facilities. It's not frequent, but it is an acceptable approach. In those cases, the utility source could be the alternate power source. So that's one case where an alternate power source could be a generator if the utility source is the main electrical power source for a healthcare facility, and the alternate power source could be a utility if a large generation plant that's local to the healthcare facilities is indeed the main power source. So the alternate power source could be either. Now, both NFPA 99 and NFPA 70 have what's called an essential electrical system. The essential electrical system includes the alternate power source and all of the distribution from that system all of the way down to the loads. And by loads, I mean perhaps the red outlet. I mean the emergency lights or any other important piece of healthcare, either healthcare equipment, medical equipment, or facilities equipment, the physical infrastructure. So those two phrases, alternate power source, might be a generator or it might be a utility in certain cases. The essential electrical system includes the alternate power source and then goes all the way downstream to the loads. NFPA 110 does not apply unless NFPA 99, NFPA 70, or another NFPA document invokes NFPA 110. And if the alternate power source is a generator, in the vast majority of cases, then either 99 or 70 or some other code and standard will indeed invoke NFPA 110. The generator set is an emergency power supply. That's the phrase. In this particular case, if the alternate power source is a generator, then the emergency power supply is also the same generator, and you have both sets of terms that apply to the same equipment. The emergency power supply system, on the other hand, is not the same as the essential electrical system. The essential electrical system starts at the generators up in the NFPA 99 and NFPA 70. and goes all the way downstream to the load. With the emergency power supply system, and this is the NFPA 110 description, it starts at the generator, whatever makes the generator run, and goes all the way downstream to the load terminals of the transfer device, which in the vast majority of cases is the transfer switch. Within a healthcare system, that means that the emergency power supply system, which stops at the load terminals of the transfer switch, does not include the power system further downstream all the way to the loads. The essential electrical system, on the other hand, does. Next slide, please. NFPA 101, the Life Safety Code, in two of its chapters. Chapter 7 is the chapter on means of egress. Chapter 9 is the chapter for building service and fire protection, which also includes utilities. Those two chapters actually invoke NFPA 110. In the case of the 2012 NFPA 101, it's the 2010 edition of 110 which is invoked. NFPA 70 has Article 517 that refers to healthcare facilities, Article 700, emergency systems, Article 701, legally required standby systems, and Article 702, optional standby systems. Rich, I believe you have a question about NFPA Article 700. Would you care to address that now?
Absolutely. So my question relates to your experience when we have a TIA that makes a revision to a section. For example, the 2017 edition of NEC had a 700.10d3, which referenced healthcare facilities and occupancies under the fire-rated section on emergency power. But then that was removed a year and a half later in a TIA. And the code officials might actually be looking at a book that has the old version. How do you see that adoption take place when there's a TIA that makes a change like that?
Where there's a TIA that makes a change like that, basically it's really up to the code official to determine. And the reason that I'm saying that is that looking at CMS, the vast majority of healthcare facilities, or at least hospitals for sure, in America are accredited. They are required to comply with CMS requirements. And CMS requirements apply to any facility that receives Medicare and Medicaid reimbursement from the federal government. In this context, the federal government is by far the largest insurer in America, at least for healthcare insurance. In this particular case, CMS adopted the 2012 codes about 3 years or so after the codes were published by the NFPA. And when CMS adopted the codes, it did adopt TIAs, tentative interim amendments, but only those which were published when CMS started the process of obtaining public input. And the reason it did not adopt any other TIAs, anything that was published after CMS started getting public input, was because its position is if the public did not participate in a review of the TIA, that means that CMS considers itself to be prohibited from adopting changes that did not receive public input. So basically, in a case like this, even the 2017 edition, for example, or the TIA that came out in 2017, that's not adopted by CMS because CMS simply is not using that version of the code yet. At some point, the industry expects that CMS will adopt a newer version. The last time it did it, it was notice and comment rulemaking. Notice and comment rulemaking took over a year. It may well be the same way this time. So the TIAs may be adopted by local authorities having jurisdiction. They may not be adopted by the federal authorities having jurisdiction, in this case CMS, or any accrediting agency that accredits on behalf of CMS. So that's something what you may have is you may have two different requirements that appear to say different things, even though one of them has been changed. Basically, in the case of two different requirements from two different AHJs or more than two different AHJs, you always have to comply with the more stringent requirement. Within NFPA 99, we have the essential electrical system type 1, 2, and 3. Type 1 is the more stringent. It's the one that applies to such things as systems that feed life safety and other types of equipment whose failure could cause severe injury to patients or staff. NFPA 110 is the standard on emergency and standby power systems. NFPA 111 is the stored electrical energy emergency and standby power system standard. Next slide, please. Within the NFPA 110 chapters, basically chapter 4 is a very short chapter. It's the chapter that classifies the requirements. And the class is the hours at rated load without refueling. Now, presently in the 2010 edition of 110, there is a requirement for 96 hours, but not everywhere. It's only 96 hours in certain seismic zones. After the 2010 edition was published, when we published the 2013 edition, that requirement was actually removed and moved to the annex. However, because the 2010 edition of 110 is the one that's invoked by the 2012 standards, then that basically still invokes the 96-hour requirement in certain seismic zones. In certain seismic zones. The type, the classification of type, is how many seconds of interruption are allowed. In most cases, for the very important loads, life safety, fire protection, and many other loads, 10 seconds is the maximum interruption that's permitted. And the level, there's two different levels. There used to be 3 levels in NFPA 110, 1, 2, and 3. 1 is the most severe level. Again, it's the equipment whose failure could result in injury. The other main chapters in NFPA that I want to talk about are 5, 6, 7, and 8. 5 is the chapter that talks about the emergency power supply. What's that? That's the generator. It's the source. It's the converters. It's the accessories that help the generator run. 6 is the transfer switch equipment. 7 is the installation and environmental consideration. That discusses, for example, what can go in a generator room, what can go with transfer switches, things of that nature. And 8 is the routine maintenance and operational testing. So from NFPA 110, there's something that is important. Chapter 7 has the requirement on installation acceptance testing. When the installation acceptance test, which is quite substantial, and not everyone understands it, but when that test is completed, the 110 requirement is be followed immediately by the first monthly load test that's required by Chapter 8. You can't not do the first load test. The first load test starts as soon as the installation acceptance test is completed. Chapter 7 and 8 also include requirements for weekly inspections of the entire emergency power supply system, load tests of the entire EPSS, annual testing only if required. That means only if the monthly results don't get the generator loading up to 30%, and a 3-year 4-hour load test, which is a flat-out requirement. The last item I want to talk about with respect to Chapter 8 is that the routine maintenance and operational testing program actually is required to comply with all 4 bullets: the manufacturer's recommendations, the instruction manuals, the minimum requirements of Chapter 8, and the authority having jurisdiction. Finally, I would like to talk about a couple of ASHE resources. ASHE is the American Society for Healthcare Engineering. For those of you who are ASHE members, you can obtain those two monographs as PDFs for free. If you're not an ASHE member, if you want the monograph, you would have to go to the American Hospital Association bookstore and purchase the monographs. But if you are an ASHE member, you can obtain those monographs as PDFs for free.
Excellent. Thanks, David. Now, one of the questions I get pretty frequently is, if I'm a B occupancy, meaning I have healthcare services, but I don't care for patients longer than 23 hours at a time. So, for example, an ambulatory surgery center where you have operating rooms that are clearly providing critical care, but it's a B occupancy. It's a common concept that we see. Well, with the B occupancy, does that mean it has to comply with 517? And it comes back to what David talked about. The category assignments still apply. If I have category 1 or 2 spaces, or types of spaces in which loss of life can occur, then that's what's going to push an AHJ to trigger 517 and NFPA 99. We also get asked about critical access hospitals. And what I'll say about smaller facilities, or anytime you have multiple occupancies mixed into one building, be aware of whether or not your emergency equipment, your EPSS or EPS, can be located in a B occupancy and then serve an I2. Typically, that's not going to be the case. You're going to want to locate that in the I2 and then backfeed the B occupancy. In remodels, that really matters. Now, David talked about alternate power sources, and what can they be? Well, we see here a list of what is typical, right? NEC allows for fuel cells and batteries, and yet NFPA 110 is going to talk about natural gas generators and diesel generators. Now, David, even though we see NFPA 853 here, what can we see coming up about fuel cells, do you know?
Right now, the second proposed basically phase for the NFPA 110 2022 edition is out there for public comment. If you go to nfpa.org/110, next edition, you can actually read what has been proposed for the 2022 edition. We're in the phase basically that determines whether or not anyone is going to want to propose a notice to, basically a notice of intent to make a motion during the NFPA annual conference this summer. Right now, the 2022 edition is proposed to allow fuel cells as emergency power supplies. Back to you, Rich.
Excellent. Thank you very much for that. Now, batteries are another concept. With the advent of electric vehicles and lithium-ion making a pretty strong play, we're seeing 15, 20-year lifespans with batteries. So is that allowed? Well, NEC 517-30B3 does specifically list batteries and references NFPA 111. Another question I get is, can I use a natural gas generator? Well, remember that there's going to be standards and codes applicable for runtime and on-site storage. If I have a natural gas line break because of, say, an earthquake, natural disaster, or even construction activities, and I lose my power source, what can I do about a backup or on-site fuel? Now, maybe it's propane. The takeaway I have in this bottom image is that keep in mind your generator, regardless of natural gas or diesel, fuel oil, might actually share some of that with boilers, for example. So when you're citing your runtimes and calculating your volumes, it's not just the generator you need to be concerned about. You might also have to take into account mechanical systems. Now, when we're loading, you've heard the term 30% minimum, right? That's going to be a manufacturer's requirement to prevent wet stacking during testing. And that's something that, as David mentioned, NFPA 110 says comply with manufacturer's testing. So we look at, are we getting enough load? And we'll talk about load banks on a slide here. But from a minimum size, I want to make sure that anything that has to be on in, say, 10 seconds is going to be able to fit on the smallest genset. So I'm going to size, if I'm doing parallel gensets, the smallest one, any one of them, to make a point, to handle all of the 10-second loads. That can include medical air and back pumps, and the elevators used for fire rescue, fire pumps, critical transfer switches, etc. So you want to make sure you're taking that sizing into consideration. And if you have a lot of extra capacity because you're doing parallel gensets, if you want to backfeed normal, take into consideration that you might have an EPA Tier 4 situation on your hands if the client wants to use that for load shedding or peak shaving. if they're going to receive financial incentives from the utility, that's usually what's going to trigger Tier 4. And whatever your strategy for backfeeding normal, ensure that the facility actually understands how that system works and that they feel comfortable using it. Now, if we're going to do supplemental generator connections, i.e. an external load bank or an external generator connection like you see imaged in the bottom left, it can look at a variety of ways. And one of which is you could actually put a transfer switch that allows for those external connections to be either a temp genset or a load bank. Now, David, what are your concerns associated with using equipment like this?
The only concerns I would have are that equipment like this requires basically human action, and it generally occurs at a time when there is an emergency in place at the healthcare facility. Several years ago, during one of the major natural disasters that was affecting the Eastern Seaboard, there were healthcare facilities that had arranged for portable generators, and the portable generators arrived, and the staff had never really trained on what to do to connect them and to get them operating properly. As a result, there was a delay in getting backup power to those particular facilities. It's really important anytime you have human interaction that needs to occur, it's really important to make sure that the people who have to do the work are able to do the work at the instant they need to do the work. Back to you, Rich.
Thank you. So I agree 100%. And that also relates to onboard versus just traditional external paralleling gear. Your staff might be very comfortable with external paralleling gear in the big sections, but now they might want to save some space and move to onboard paralleling. Well, that puts the controllers themselves that have the logic on the gensets, and maybe that's not where they want to stand or where they're used to standing to operate systems. So you might need an alternate display or a copy of the engine generator controller inside a location, like I show on the bottom right. Just because we're doing onboard paralleling doesn't necessarily mean that we're going to eliminate all of the gear and eliminate a whole electrical room. It just means we're shifting some of that location and how big some of that gear is. Now, I love transfer switches. They're one of my favorite parts of this whole system, right? They are what define each of those individual branches. And they do a lot of work, but there's a lot of options. One of the things I'd like to discuss with you is planning for space. Bypass isolation adds a lot of physical space into that electrical room. It sometimes doubles the size of the switch. So in your sizing of space, whether or not the client says, I'm on the fence on bypass isolation and closed transition, at least think about what is your worst case footprint and realize they might change their opinion later. I like bypass isolation for the reliability of maintenance and not losing the loads. Same thing for closed transition. I like it for basically transferring from emergency back to normal and not having a blip that drops every computer. Is that a problem for a hospital? What about when motor overloads trip out because when that few cycle of difference that an open switch has comes in at a different phase? Maybe it doesn't do it all the time, but doing it a couple times might be enough of a reason to move to closed transition. A 3-pole versus 4-pole conversation could happen over an hour. The takeaway is, if you're going to go into a remodel scenario, pay very close attention to what's already there and make sure that you vet that system to ensure what's separately derived and what's not, and do I have any accidental or intentional ties between neutrals in the same system. This relates also to N+1. If I'm going to have one big critical transfer switch and that one switch fails or hangs up, I've lost the whole facility. We'll talk about, category 1 and 2 and alternate sources in a little bit here, but the more switches I have, the more load shedding capability I have on the equipment side. And that's going to be cabling as well. Now, ATSs or transfer switches have a variety of cabling requirements to them. Now, keep in mind, 2017 NEC says that we now have to monitor the integrity of the start conductors. And doing that might actually add a third conductor. So if you're complying with 2017 NEC, because maybe you have multiple things to comply with, not just CMS, but maybe also a local jurisdiction, and they want to see that third conductor, you have to plan for it, as well as any fire rating or 2-hour rated protection that those conductors might have. There's a variety of communication protocols. We might want switch position and source availability both at a piece of paralleling gear. If you're going to do load shed through transfer inhibit, that's also additional conductors. An elevator pre-signal requires that you actually have cables that connect the ATS to the elevator. Sometimes that gets missed. Now, David, how do you feel about the future of using the internet to connect transfer switches to a facility for enunciation?
With respect to enunciation locally and enunciation outside the facility, unfortunately, for those who are basically fall under the CMS requirements at this point, that would be the 2012 codes, which have invoked the 2010 edition of 110. The 2010 edition does not presently allow this sort of transmission, this sort of connectivity for the emergency power supply section. The good news is, moving forward, that the 2013 edition does. So as soon as CMS adopts a future edition, future being anything newer than the 2012 Life Safety Code, then we'll be able to use an edition of 110 that also has this type of communication back and forth.
Excellent point. I like that. Now, we probably all have sat through hour-long sessions of selective coordination in ArcFlash. I'm not going to reiterate all that information, but I am going to bring upon something that I'm personally concerned about, and that is how arc energy reduction systems can have a negative impact on selective coordination. If we look at this graph on the right here, if that far breaker to the right has arc energy reduction, and you see that bottom instantaneous tail, and I crank it down when I flip that maintenance switch, and that tail moves all the way to the left and starts to clash with the downstream breakers, I've essentially lost coordination in instantaneous range. Now, that matters to me in certain healthcare applications. Does it matter that I lose selective coordination? I like coordination in general. So a maintenance mode switch that gets turned on, what if it gets left on? Does anybody know that that got left on? If I have zone selective interlocking, or ZSI, and is that sufficient? Because that's actually capable, it's one of the required ways that you can meet the arc energy reduction, because you're coordinating your breakers not through the trip settings, but through a timing signal. And that applies for only the breakers that have ZSI, not the big molded case breakers that might be downstream. So I want the takeaway here to be for engineers, when you're applying codes, you're still looking holistically and trying to build the most redundant and reliable system that you possibly can. Now, speaking of redundancy and reliability, David, I think you got something to say about common mode failures.
I surely do. I've been in this business more than 45 years. And part of my experience is that I have been the hospital engineer working within healthcare facilities. And I've seen, both in my own hospitals and as a consultant, that there are common mode failure vulnerabilities. And what do I mean by a common mode failure? Basically, think of it this way. Any part of let's talk about the emergency electrical system. Any part of the central electrical system, as an example, using the code phrase, that where you've got redundant equipment in the same space. Say, for example, two critical branch transfer switches that feed different critical branch loads that are, the loads themselves are considered to be redundant to one another. The switches are redundant to one another. But let's say, for argument's sake, that they're in the same room. Something happens in that room. In that case, the two redundant switches are gone. It doesn't really matter that you have two redundant switches. Let's talk about multiple generators being fueled by the same fuel source or the same fuel pump controls. In those cases, and this is not an uncommon situation. This is actually probably one of the more common design practices in America. And in cases like this, you may well have two different fuel pumps, but if the two fuel pumps are on the same skid and get their power from the same control panel, which may well get its power from the same branch circuit, then you have the potential for common mode failure. Talk about different subsystems. Let's say your subsystem is, for example, critical branch, or to be a little bit more precise, you have a riser or a couple of risers coming out of the distribution panel further downstairs. If you lose the distribution panel, you've lost both risers, even though the two risers may well have been intended to be redundant to one another. Same thing with paralleling switchgear. You have 4 generators all tied into the same paralleling switchgear. In cases like this, and this is the most common design thing in America, having this sort of situation. In a case like that, let's say the paralleling switchgear fails. It's rare, but it can happen, and sometimes it does happen. In those particular situations, there's the potential for common mode failure. So what do? How do we deal with those issues?
Well, that's a good point. When we look at how do we break apart these systems that are so commonly located in a single room, one idea might be to take that double-ended unit substation that we've always considered to be the best option and break that into a main tie-main arrangement and put them in 2 physically different rooms. Are we giving up some space in the facility? Yes. But are we gaining resiliency? Also, yes. If you have a really small facility and you have a single 150 kW genset, code says, you know what, you can use just one switch. Now, does that make sense? Depends on the application. It depends. That's the answer, right? We have to know whether or not we're going to sacrifice that kind of redundancy, right, David?
Yes, sir. It really does. And I know that well, it's funny. Amara is counting. It depends, and we're now up to 2, Rich, so we better be careful. Let's talk about contingency planning. I mentioned this before. So any piece of equipment can fail, and the piece of equipment that fails might be one with common mode failure potential. Whether the failure is a generator or a lineup of paralleling switchgear, which may well cause the inability to take the power that's coming out of multiple generators until that particular issue is solved. Over the years, I've heard a number of people say, I don't care about the normal power because I've got a generator. Well, the fact is that whether you have a generator or not, whether you have emergency power to a transfer switch or not, the transfer switch has to operate properly when it's required to, or as long as it's required to. It's like any part of emergency power. Whether the transfer switch feeds the critical branch or the life safety branch or the equipment branch, or in the smaller facilities, a branch which might feed more than one of those 3 types of loads. In those cases, any switch can fail. Any transfer switch can fail. The transfer switch, any one of those 3 branches, you've got normal power coming into it, and you've got some form of emergency power coming into it. And as long as the transfer switch works, then it will deliver power to the wiring that's on the load side. What if the wiring on the load side fails? It can happen. It's rare, but it can happen. Very frequently, we have multiple generators, and the multiple generators are generally all in a similar room if they're all indoors. I've seen these rooms are gorgeous. I mean, I'm an engineer, I could say that. But what happens if the generator room becomes untenable? Or if you have, say, 12 or 15 or 30 transfer switches in a transfer switch room, and the room becomes untenable? Or the distribution pathway itself, whether the distribution pathway is from a generator to a paralleling gear, from a paralleling gear upstairs in a high-rise building, from a transfer switch up to the distribution panel. any one of those distribution pathways can fail. And with that all in mind, there's a lot. Basically, those are the things that need to be taken into account.
That's right, David. I mean, when I look at these images here, I have to ask myself and ask my client, where do you want resiliency? You know, sure, NEC and NFPA 99 are going to talk about critical care and general care, but that doesn't apply to all facilities. And as David mentioned, we can have all kinds of failures. We can have islanding problems in which we actually lose connection to the entire facility. And that could be an entire discussion in itself. When we do branch circuit redundancy, I'll ask my clients, here's a list of all the departments in your facility. Maybe there's more or less. What outage can you tolerate? A second, 10 seconds, an hour, or even a day? You know, do we want critical switch 1 and critical switch 2 to serve that same space? What kind of outages can we tolerate? And that's going to directly tell me, here's the amount of resiliency and redundancy I need to build in. For example, a lab doesn't have to meet the patient, space requirements of normal and critical. But if you ask the lab, hey, can I shut down power for an hour? They're going to say no. In which case, the outage they can tolerate is moving a plug from outlet A to outlet B on a separate branch. And all of that comes back to how do we mitigate this? I mean, the image on the right is what it looks like to pull wire inside of a conduit at 400 amps per phase. So if an engineer says, I would like an 800 amp breaker in that existing critical distribution panel, what does that physically mean to the facility? What are the outages? I want us to get away from just showing dashed lines and actually having outage mitigation plans. How long is this going to last? And what impact does that have on the facility? What does that have on the department? Is that serving an ICU wing? Can that ICU wing go down for 2-3 hours? The answer is probably no. So if you need to plan a relocation of patients, or if you're going to shut down elevators for a couple hours and those elevators need to take patients to the OR, what are the contingency plans? You have to have those talks with your owners ahead of time. And lastly, we can't have a slide in 2021 without talking about the impacts of COVID-19. And what I'd like to say briefly is that what we're seeing is owners ask for resiliency and flexibility in the acuity of their patients to say, I would like more negative pressure rooms. Well, if we're going to do that, should we also electrically be saying, I want any room to be defined as critical care, even if most of the wing is general care? Should I design any room to be an ICU? That's going to affect our transformer loading, and therefore it's going to affect our electrical room sizing. Now, David, what do you have to say about any of the future impacts that you see?
One of the biggest things that I'm going to see moving forward is that I think we're going to see more technology connected to emergency power, not because the codes say to do it. I think we're going to see more islanding moving forward, simply because healthcare systems may well be looking at this as a business decision.
All right, excellent. Thank you, gentlemen. Now let's take some questions. Please type your question into the Ask a Question box, typing the presenter's name before your question so that I know who should answer it. We will get to as many questions as time allows, and responses that we don't get to will be posted online at www.csemag.com as a Q&A article. To download the presentation slides, use the Event Resources tab on the left side of your screen. And as a reminder, you may earn one AIA CES approved learning unit for this session. You do need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, please use the Learning Unit Exam tab on the left side of your screen. The exam will open in a new browser window. And have you ever heard of CFE EDU? Click on that link on the downloadable PDF to register for free courses on smart buildings, critical power systems, and designing electrical systems and rooms. Registration is required, and you can take courses at any time. All right, so David and Richard, it's time to answer questions about this topic. As I mentioned, please type your question in the Ask a Question box, and we'll get to as many questions as time allows. All right, David, I'm going to send this first question to you. Is CMS the agency that is responsible for recognition of reliable natural gas as a bona fide reliable on-site fuel? And if not, where does it come from?
From what I've seen so far, CMS is not taking a position on that. I heard that at least one state has taken a position. The state of Florida, I believe, has taken that position. They've determined whether or not it's reliable and the degree to which natural gas has to be on site. I'm not aware of other states, but I believe it would probably be a state or local decision making.
Okay, so to answer that question more succinctly, it depends. Got it. Okay. All right, let's see here. So Rich, I'm going to send this next question over to you. So we're talking about hospitals, and the whole hospital is backed up by a diesel generator. Can all of the utility power and all the generator power be applied to the ATSs and then distributed? Or is redundant power, I mean, can you talk a little bit about this, please?
Absolutely. And we get this question a lot. You know, if you're looking at resiliency of a hospital system, maybe you're doing a greenfield standalone hospital and you get to build this thing from scratch. And the utility says, we can give you 2 feeds coming in. Well, that's great. I would like to have 2 feeds coming in. But maybe they say, you know, I can only give you 1 feed and I can't guarantee it's going to be up all the time because we like to have tornadoes here. In that case, the facility might say, well, let's go ahead and do some tier 4 big, 15 kV, say, gensets that just take over for the utility. Now, what does that do for the rest of your discussions that we've been talking about on what kind of transfer switch branches you'll have? Well, remember that we're still looking at resiliency. If you're going to have just 1 or 2 or single pathways, you're going to do that common mode failure analysis and what things can fail. The one thing I have experienced is that it does ease the conversation sometimes on, does it have to be on all emergency, or can we actually put some more of the stuff back on normal? So sometimes there's actually a cost savings that can happen when you're doing the 15 kV utility backup, because you feel like your normal is now more resilient than it would be otherwise. And you can go to maybe a more code minimum approach for normal and critical instead of critical 1, critical 2. But it depends, because you're going to have to perform the risk analysis defined within NFPA 99.
Aha, it depends. Thank you. Alrighty, so Dave, this next question is for you. Which code mandates the length of time a generator is required to run without refueling? And very specifically, can you discuss the Class X designation? Okay,
so basically the codes, for example, the Life Safety Code has 2 chapters that invoke NFPA 110. And in at least one of those chapters, it talks about how many hours the generator needs to operate for that particular type of load, which I believe was the means of egress. That's the emergency lighting for the means of egress. There are different requirements in different codes and standards, and those requirements they're not the same. Basically, you have to look at what applies to the facility that you are concerned with and what are the rules, and follow those rules. In the event of 2 different rules, with one being more restrictive than the other, you must always go with the more restrictive.
All right, good to know. Thanks, Dave. Rich, this next question is yours. We're talking about limited care facilities such as hospice facilities. Do I have to sort out the branch circuits by critical, equipment, and life safety?
So we get this a lot too. Now, when you look at, say, 517.40, when you start getting into essential electrical systems for nursing homes and other limited care facilities, you're going to see that it actually changes the figures. The figures show 2 switches instead of 1. It'll show a life safety and an equipment branch switch, and it doesn't necessarily show a critical switch. It doesn't show 3, it shows 2. Now, of course, this comes back to risk assessment and just determining how many of those equipment branch, quote unquote, switches you're going to have in your limited care facility, and if you're actually going to treat some of them more like critical and equipment or just go minimalistic. And I see both approaches being used. It does also depend on the acuity of those patients within there and what the staff is used to seeing. You'll have some staff that's just used to seeing all three branches and wants them, in which case that's a labeling issue. But pay attention that 517.30 and 517.40 and those sections that follow are different because they apply to those different facilities.
All right, very good. Thank you. Dave, this next question is for you. Would you please tell us the difference between NFPA 110 class and the requirement or recommendation for on-site stored fuel runtime? That's a big question.
Okay, so basically, the on-site stored fuel runtime is that's determined by the code, and the class. And I made a couple of notes here, and I want to try to find that page, and of course I can't. Oh well, it is what it is. Basically, the amount of fuel that is stored on site is determined by what the code says for how many hours you have to run the generator at full load. In most cases, it's at full generator load. And that's the criterion. It's determined by the codes and standards. It's determined by the authorities of its jurisdiction. In some cases, it's determined by the state. In a lot of cases, there's no particular requirement for so many hours of runtime coming out of the national documentation, but different states have different requirements.
All right, thank you, Dave. It looks like we have time for one last question. Rich, I'm going to send this one over to you. Can you please provide some examples when ground fault protection not required by code could benefit critical power supply systems?
Yes, thanks, Amara. Now, we want to be careful because when we're doing ground fault, yes, that's a requirement on the normal side. And if we're talking healthcare facilities, then we're looking at selective coordination requirements. So that means we're going to have the main and the branches. Now, NFPA also explains, and NEC does, that that's not two in series. It's not two main breakers in series. It's the main and the branches because the intent is selective coordination. We want to maintain selectivity so a ground fault on a branch doesn't take out the main. Now, when we're looking on the emergency side, we're interested in knowing, do we have a ground fault? But we're not required to trip on that. Instead, we would like to get an alarm. So your LSI-G, right, your G is your ground fault. Your LSI-A is going to be your same breaker, except I'm alarming instead of providing an actual trip. And that's important because we're considering that we want to know we have a problem. But if we just shut the generator off because it has a ground fault, we could actually be doing more damage than what we would if we were to try and save it. You know, imagine shutting down the generator on an entire hospital campus while that's the only power source and the hospital goes completely dark. So we want to know. It's a good question because we want to know if we have a ground fault, but we want to alarm in that condition. We don't want to trip the entire system in that condition. Any individual ground fault requirements are also listed in NEC, and those would be at the branch circuit level, but not shutting off the entire facility. Thanks, Amara.
Yeah, well, thank you. I'd like to wrap up by thanking these extraordinary subject matter experts, Richard Vedvik and David Steinmetz, for sharing their extensive knowledge of power in healthcare buildings. I'd also like to extend a special thank you to Cyber Sciences and Kohler for supporting this education session. Before you go, we need your feedback to improve future education sessions. A short survey will pop up on your screen as soon as this webcast ends. Please take a few seconds to complete it. Finally, on behalf of Consulting Specifying Engineer and CFE Media and Technology, thank you for joining us, and we'll see you again on the next education session. Goodbye.